So, good afternoon. My name is Holger Meyer. Welcome to the physics seminar series for the fall semester 2025. The physics seminar is sponsored by April and Eddie Lucas. So once in a while we bring in external speakers who have travel costs. Today, though, we have Tyler Nolan, who didn't need to travel far. He's from Wichita. But before I introduce this week's seminar speaker, Olaf wants to make an announcement about the Society of Physics Students. So, Olaf, please.
Hello, everyone. I'm sure you all probably know, but tonight the Society of Physics Students is having our retro game night. So I would love if anyone and everyone could show up at least for a little bit. It's from 5:30 to 7:30, but I'm sure it'll go a little longer. We will have food, free food, so you can come sign our sign-in sheet, get some free food, play some retro games, maybe watch a movie. We'll see what's going on, but it'll be fun. So at least show up for a little bit and support your physics club. Thank you.
Thanks. Yeah, indeed. So Tyler Nolan got his physics education here at Wichita State. It is undergraduate, and then joined the master program and finished his Master of Science in Physics this summer. The last stretch of it was funded by the Evelyn Schneider Hall Summer Fellowship. And one stipulation of that fellowship is that the recipient present their research during the following fall semester. And so Tyler is here to fulfill that requirement and let you all know about neutron detection with GAGG crystals using double pulse methods. So give it up for Tyler.
Okay. Thank you, Dr. Meyer. Kind of like Dr. Meyer said, I had the pleasure of doing my education here. He was my advisor, and I ended up being able to work with the NSOL group. So I kind of want to talk a little bit about that and the research that I did for my master's thesis and show you guys a little bit about that. So I want to start with a little bit of an introduction to the NSOL collaboration. And with this group, they deal with neutrinos. And I'm sure a lot of you are familiar with neutrinos, but they're low mass particles and they have a neutral charge and they rarely interact with the world around us. The solar neutrino flux here on Earth would require you to have a very large detector to study these solar neutrinos. However, this problem can be fixed with a smaller detector journeying closer to the sun due to the inverse square law. So that is kind of the goal of the group and what the work that the group primarily does. However, the work that I did is with neutrons, not neutrinos. And how does this relate? Well, I guess the answer to that would be GAGG. So GAGG stands for Gadolinium Aluminum Gallium Garnet. It is a type of crystal, and it is the chosen scintillator for this group. And a scintillator basically just means that when a particle interaction occurs within this crystal, that the crystal fluoresces or releases a small amount of light that is then read off to a PMT or a SIPM. So in the case of the testing of what I did for my thesis and this summer, it would be a PMT and a SIPM. We did testing for both. And the importance of doing that, particularly, is that neutrons are a background particle in space. So for this neutrino experiment, we want to know whether this neutron signal will be disruptive. And as well as that, gadolinium, which is within the GAGG crystal, also has a high neutron capture cross section. And in knowing that, since we already know it'll be a good neutrino detector, we also could have this as a multi-use detector. So it could detect charged particles, it could detect neutrons, and then it could detect neutrinos. And in doing that, this could be useful to the ISS. So instead of having several different detectors, they could have one that does several different things, and they could use that on the ISS, or they could use that on off-planet missions. So on the moon, on Mars, I mean, it would be reducing the payload costs anywhere, essentially. And an example of neutron detection playing a crucial role before is on NASA's Lunar Prospector mission, which used a neutron spectrometer. And this was essentially utilized to map the hydrogen enriched deposits on the moon. And in doing that, it provided evidence of the water ice at the lunar poles. So neutron detection in space is something that is useful. So if you look here, this is the neutron capture cross-section for gadolinium, specifically the isotopes that I was interested in with my research and the group was interested in, and that's gadolinium 155 and 157. So I guess I don't have a pointer, but the area of real interest is around that 10 keV area. So, oh, yeah. Okay, yeah, that's a good idea. Wait, do you guys see it on there? Okay, yeah. So that area right around there. So that's where I focused a lot of my simulations, and um, and I wanted to see everything below that area. While all of this does tell you good information about what we're looking for, it doesn't necessarily tell you what a neutron is. So I guess I'll just do a little slight introduction of that, and that a neutron is a subatomic particle, and they're found in the nuclei of an atom. And they're charged neutral, and it was first theorized in 1920 by Ernest Rutherford. Rutherford essentially theorized a particle to accompany the proton, which was discovered in the nuclei, but there was a missing amount of mass, so they didn't know what that mass was coming from. In 1932, however, James Chadwick was able to confirm it experimentally, and where he used a polonium radiation source, and he essentially aimed it through a beryllium disk, and he was able to get this unknown radiation. The radiation was then going through and releasing protons into the detector, and he was able to work backwards, essentially, discover the kinetic energy of this radiation, and fill in the missing piece of this puzzle, which was the neutron. I also want to tell you a little bit about neutron detection as far as it goes with several different ways it's currently being done comparative to this way, just so you have a little bit of background on that. So one way is helium-3. Helium-3 is a gas detector, and it's actually the most common. However, it's become quite expensive due to the helium scarcity. And this reaction essentially is not a capture, but actually a charge transfer. So you have helium-3, the neutron goes in, you then left with tritium and a proton. So this proton is then picked up in the ionization chamber by the electric field of the anode and cathode. You then have neutron detection with boron-10. Now this one actually is a capture, in which this can be done either with the gas, borium trifluoride, or lining the inside of a detector as a doping agent. And what happens here is you have boron-10, the neutrons captured, you're left with lithium-7 and an alpha particle. This can also be done with lithium-6, primarily used in crystals or in lithium glass, so lithium glass-based scintillators. And this one, you have lithium-6, you have a neutron, left with tritium and an alpha particle. And again, it's of note that all of these methods that we're talking about previously result in a single pulse, not the double pulse method that I was investigating. And you can see these neutron capture cross-section comparisons here. So the GAGG, especially at these lower energies, is higher than using the most common, the helium-3 or any of the other methods. I also want to take of note too the natural abundance of the gadolinium. So gadolinium 155 and 157 make up about a third of all natural gadolinium. So that it is important too with us using these GAGG crystals. And we can now talk a little bit too about the neutron capture and how it happens on gadolinium 155 and 157. So with gadolinium 155, you're going to have the free neutron enter. You're then going to have gadolinium 155 proceed into gadolinium 156 in an excited state. This isotope then de-excites, releasing, well, then you're having gadolinium 156 and it releases these gammas of various energies. And these gammas of various energies are what we want to detect in this detector. So you're going to have a similar situation happen with gadolinium 157, in which the neutron goes in, is captured. You're left with gadolinium 158 in an excited state. This isotope then de-excites gadolinium 158, and then you have the gammas of various neutron or of various energies. And these are the primary and secondary gammas for the gadolinium 155 capture. It is of note that all of these add up to this primary gamma ray energy, and all of these, or most of these, have primary pulses along with secondary pulses, and some of them even tertiary pulses. So seeing this double pulse method, you should be able to detect a large amount of these. So now to kind of talk about a lot of the research that I was doing and the experimental setup of what was done for my thesis. So in order to do a neutron study, you're going to need several things. You're first going to need a neutron source. So in our case, we ended up using an ambi source. That stands for americium beryllium. And essentially how that works is there's americium inside of it, americium 241. It goes into beryllium film. This then releases carbon 12 and a free neutron. And that free neutron is the neutron that we then want to capture with this GAGG crystal. But as well as that, you'll need a shielding source. We ended up using lead, and you'll need a layer of a moderator material. And this is just to thermalize or slow down these neutrons, because a lot of them are going to be fast and high energy and will not necessarily be able to be captured inside of these GAGG crystals. So you want to slow some of these down so that they can then be captured inside the GAGG crystal and detected with the GAGG crystal along with a PMT or a SIPM. This led to me doing primary simulations. For the shielding, I tested both lead and polystyrene at first, and I tested them in increments of 5, from 5 centimeters to 80 centimeters initially. And this was just to get an idea of what area would be good for me to use and what would be best. And we did this with 100,000 particles of both neutrons and gammas that were tested. And you can kind of see the setup there. So this is the primary shielding simulation constructed for one of the lengths. And essentially, it has to make it through the shielding to get to the detector, and the detector was just polystyrene in this case. It didn't necessarily matter what the material of the detector. I just want to see if the gammas and neutrons are able to make it through this shielding material into that detector. And I guess it's also of note that I didn't really talk about that we're using JAONT4 for these simulations. So JAONT4 is, for those of you that may not be familiar, is a tool that particles physicists can use that can simulate different particle interactions so that you have an idea of what they'll do in the lab. So by getting the data from that and then plugging it into this equation where I have the percentage of neutrons and the square root of neutrons and gammas, I'm then able to get the figure of merit for the amount that is ideal of the length of shielding. So as you can see there, this is the figure of merit, and it shows that at the larger lengths of paraffin, or not paraffin, of lead and polystyrene, that you're not getting very many of the neutrons, because you don't want to cancel out all the neutrons, but you also don't want to allow through the maximum amount of gammas either. So there is a very important, I guess, ratio there. So that's what I was looking for, is the ideal ratio for that. And doing that, I then went through, did the experiment again, or the simulation again, and I did it for 0.1 centimeter increments. So this was a test of 0.1 to 10 centimeters, since I now know that the area of interest is up here in this 5 to 10 centimeter range. So this is essentially a zoom in of that previous range on there. And I find that the most primary area of interest is right around this 3 centimeters area, 2.8 to 3.1. So that is where we're going to get the ideal ratio of letting in the most neutrons that we can while blocking out the most gammas. So this takes me then to the spear simulation, which I did. And the spear simulation essentially has 0 to 3 centimeters of lead using the previous simulation results. And I then had a length of 3 to a variable of paraffin. I was using paraffin as the moderator material to thermalize the neutrons, but I don't know how much of it I want to use. So that is why we're going through and we're having a variable of it to see which length of it is ideal. And there was also a third spear added in of 1 centimeter of polystyrene. And this was just simply for the veto. Now it is of note that we did not end up using the veto in the actual experiment, but at the time of simulation, I didn't know that. So that is why there is a veto added on the spear simulation. And essentially with this one, the neutrons will start in the middle of the spear. They'll then go out, make it through the lead, make it through the various lengths of paraffin. And once they make it through the polystyrene, they're then counted as an event. So I want to get the maximum amount of events for these different amounts of paraffin to see which one is ideal. So with these moderator results, each of these runs consisted of 1 million neutrons, and they were done in 1.2 centimeter increments. And that too was just because the paraffin discs that we had in the lab are in 1.2 centimeter intervals. So 1.2, 2.4, and etc., all the way to 15.6. And I was then able to get this data with the 1 million neutron runs. So in this data, you'll see the area of interest that has the highest amount is right around this 8 area to the 7 area. So almost 7 centimeters and 8 centimeters. However, this is with the whole spectrum of neutrons. If you'll remember back to the 10 keV and below area that I said was of primary interest to my research, if I then tested that area, you'll see that 6 centimeters is the ideal amount. So by looking back into that below 10 keV increased neutron capture cross-section area, that then tells me that 6 centimeters was the route to go. So once I know the amount of moderator material to use and the amount of shielding to use, I can then have a simulated lab setup. So this is a picture of the lab setup that was constructed in GAGG, and this just consists of a lead cylinder in the middle that's 2.54 centimeters and 6 centimeters of paraffin, followed by a small GAGG crystal there. And the GAGG crystal is of the dimensions of the same one that we used in the lab. The lead, which ended up being the 2.54 centimeters instead of the 3, is just because that, again, was lab constrained. So when we looked in the lab, we ended up having a cylinder of lead that actually was 2.54 centimeters. So that's the one that I ended up constructing inside of GAGG. And doing that, I then ran this simulation with 216 million neutrons. And the reason for that is just because the ambi source that we used had released about 2,500 neutrons per second. If you do some multiplication, that ends up to 216 million neutrons a day. So this is essentially a day's worth of neutrons. And doing this, we find that approximately 3.55% of the neutrons were able to make it to the GAGG crystal and deposit some energy. Of those 3.55, or not of the 3.55, but additionally, 0.12% of these events are 10 keV or below. So both of these are areas of note. So we have the original 3.55 that are making it, and then we have 0.12 that are in that 10 keV and below area of being captured. So it is of note within the simulation too that at this point, none of these are being captured. So the simulation right now is just logging the energy. However, the same simulation was then run with the ability for the neutron captures to take place. And that was done with 2 lengths, 6 centimeters of paraffin and 3.6 centimeters of paraffin. And that was just done simply to, well, for 2 reasons. One, to show the amount that we expect to get captured from the 6 centimeters, but also compared to 3.6, just to make sure there was an increase that we thought there would be based on the previous data that we got. And doing that, we do indeed see an increase in the amount of neutrons captured. So the thermalization in the simulation was working because you have a larger amount of neutrons that are captured at 6 centimeters than you have at 3.6 centimeters. So a simulation was also done for tungsten epoxy shielding. And this simulation was just done to test the amount of neutrons that were expected to pass through it due to this being the shielding that is used for the Snappy 3U CubeSat. So this was done with 1 million neutrons, and they were just emitted in a beamline at the shielding, and any of them that were able to make it through the shielding were counted as an event. So that resulted in about 92% of the neutrons making it through the shielding with the ambi neutron spectrum, and 93 of them using a spectrum received from the ISS from one of our colleagues. So right around the same area for both of them are able to make it through this tungsten epoxy shielding. The tungsten epoxy shielding was also tested as a moderator, and this is just because the epoxy has a large amount of hydrogens present inside of it, so it could make a decent moderator material. So I wanted to test that out in simulation. So again, going back to the spear simulation, I just ended up putting 6 centimeters of epoxy in there and replacing the paraffin. It is of note too here that I did not go through and test each individual amount like the 1.2 centimeter amounts before. So there could be a number of epoxy which is more ideal than just 6 centimeters. This was just a test that was done in addition afterwards. And what was found here is that there is a decrease in neutrons, making it past the tungsten epoxy moderator comparative to the same length of paraffin. So you didn't end up with as many events. All right, so everything I've been talking about before this has been simulation. So now we're going to get into the actual lab setup of the work that I did. So in this lab setup, you'll see here I have the 2.54 centimeter lead crucible right there. And there's then 6 centimeters of paraffin and the detector inside of this box. So this is a picture of that lab setup inside of the copper Faraday cage. And the reason we're using this box and it has black tape on it is just because this is a light sensitive experiment. So with it reading the scintillation light of the GAGG crystal, you don't want light coming in and overloading the PMT or SIPM that you're using. So you're going to need to have a light tight setup essentially. So that is why we ended up using the box and the black tape. So inside of that box, this is the setup that you're going to be looking at. So there's the 6 centimeters of paraffin that are going to be used to thermalize the neutrons that are coming off of that ambi source inside of the lead crucible. And then there is the GAGG crystal that was covered in reflective foil and black tape as well, additional black tape. And then you're going to have in this case, it's the PMT board because this is the setup for the PMT and the electronics that are needed to read it out. So even having this, you are going to need a calibration curve. That will be the next step, is to have a calibration curve. And this is needed because the detector itself shows a voltage for every event. However, this voltage corresponds to an energy, but we do not know that energy without going through and making a calibration curve for it. And how you do that is you have gamma ray sources which have known energies, and you then try them with this detector first before doing the neutrons. So in this case, I used several. I used sodium 22, cesium 137, cobalt 57, manganese 54, and zinc 65. So these are all gamma ray sources that produce a known amount of energy. So in the case of sodium 22, it has 2 peaks. It has the 1275 and 511 keV peak. The cesium has the 662 keV, and so on. So then by taking that information, having each of these do a run with this detector, you're then able to have an energy that corresponds with the voltage that was read out. So this was also done with the SIPM, and the SIPM was used, however, in a aluminum Faraday cage instead of a copper Faraday cage. And because of that, we were not able to use the 2.54 centimeter lead crucible, but had to use a 2.5 centimeter piece of lead instead, just because this Faraday cage was a lot smaller for this setup. But it still keeps consistent the 6 centimeters of paraffin as well as the GAGG crystal inside. So but this did have a new data acquisition system as well as the aluminum Faraday cage. So this was done with the red pitaya. This also needed a calibration curve, however. Again, the detecting method, as far as that goes, is going to end up being primarily the same. So with this one, again, the sodium 22, the cesium 137, manganese 54, zinc 65. However, you are able to read out some of these smaller energies with the SIPM comparative to the with the red pitaya, I'm sorry, and the SIPM. And because of that, we were able to use a barium 133 source, which has an 81 keV peak and a 31 keV peak. So once we have both the detectors calibrated, we're then able to do a neutron study on them. Not a double pulse method, but just looking to make sure that we're even able to see neutrons with these two detectors. So this was the run for the PMT. This was done over the course of approximately 20 hours for each run. And you'll see here a area of interest of 0.8 volts, which corresponds to 3.78 MeV using that calibration curve. So this was the readings that I got in red with the ambi source, in black with the ambi source and lead, and in green with the ambi source lead and paraffin. So it is believed that these are still gammas because of the fact that you see a decrease and not an increase, adding the thermalation or the moderator, so the thermalizing material and the lead. However, using the SIPM, we were able to see an increased raise at the 20 volt nanosecond or 85 keV area. So there's kind of an arrow right there. And this is using the ambi source and lead, and using the ambi source lead and paraffin in green. So adding the paraffin in showed an increase, not a decrease this time. So because of this note, this more than likely is thermalizing these neutrons to the point where we are seeing an increase in the amount of events. All right, so now that we have done this, we are able to go through and look at double pulse events. So a double pulse event was basically characterized by a spike in voltage followed by an additional signal. And these are what was counted as a double pulse event. So these are two examples. The first one here, you have the detector going along. It has a increased reading in voltage, then a second increase in voltage right there. So this is an additional event right here where you have an increase in voltage, doesn't finish going back down, but you do have an additional increased detection or in voltage right there. So the detector was detecting something in these cases. And doing this, these are the events that we are looking for. So these are only two of them, but these are what all of these events were looked to be like. And doing that and using a program to log these events and separate them by the time duration, we are then able to find these over the course of approximately 1 week. So each of these runs is 1 week. So there was a background run, there is a run with lead, there was a run with lead and 6 centimeters of paraffin, and then there was a run with lead and 3.6 centimeters of paraffin. So if you look at like the 500 nanosecond to 1 microsecond there, you'll see that there is an increase in lead and 6 centimeters of paraffin in the amount of events that you get, in double pulse events that you get, as opposed to the background, the lead and 3.6 centimeters of paraffin. Additionally, with the 300 to 500 nanosecond area, you'll see that there is an increase there. So there is an increase in those double pulses in these areas, which shows that that neutrons are being detected. So the double pulse study was then also done with the SIPM. However, it was done a little bit differently. And for the SIPM, each of these runs were done for different times, but then normalized to the same, to the counts per second. So by having that and by having the change in time, we're then able to see that each of these for these runs, which there was just the lead only, which doesn't have much of anything, the ambi-source and the ambi-source lead and 6 centimeters of paraffin, and the ambi-source lead and 3.6 centimeters of paraffin. These keep the same shape. However, you do see an increase in the amount of counts or events per second in the ambi-source and the lead. So what this tells us here is that we don't necessarily see the same things that we saw in the PMT, where there was a increase in double pulses there. You're not seeing that same increase within the SIPM. So, I mean, in the conclusion of this research and the conclusion that I came to essentially doing my thesis is that while none of the energies from the initial gadolinium 155 table were seen, I think I can go back and show that table. Yeah, so while we did not see an exact correspondence to any of these primary and secondary gammas from gadolinium 155, it is still of note that we did see an increase in the double pulses in the PMT. And we saw a neutron peak in the SIPM, particularly at the 85 keV area as well. So this does require additional testing, but the ability to see double pulses is there, and the ability to see neutrons is also there with the GAGG crystal. So in that way, I was able to answer those questions definitively, even though there is more research and testing that needs to be done in this area. Yeah. So I also wanted to give a few thank yous to the Hall Schneider family for the summer support and for giving me the support to finish my thesis, as well as WSU for the previous support that I had throughout this whole time, and NASA too for funding this research, because without any of these people, this wouldn't have been possible. So.
All right, thanks for a nice presentation, Tyler. We have time for some questions.
NASA also funded us because they wanted to make sure that this GAGG counter, which has gallium and beryllium, wasn't a major background for our neutrino signal. How did you come to that?
After going through and doing the research and talking with everyone in the lab, it should not be an issue. The signals look different. So. Okay, yeah. Yeah, exactly. And I think you had one too, Dr. Muther.
If you were to continue this line of investigation, what are the next steps to try to improve things?
Okay. So there's several actually, and I know Brooks has been taking on a lot of my research since graduated. But one of which is trying several different moderator materials. So in the case of what they're using right now, or what we're using, I mean, I guess I'm still slightly involved, but not to the extent I was before. But we're using HDPE, so high density polystyrene or polyurethane, and as well as that, a different detector setup. So he does not have the where I had the shielding beforehand, that was blocking out a large amount of the neutrons, I guess. So he has since moved the shielding to a different stage of the detector. I think it's right in front of the detector now. So, and I think he's also had some pretty promising results with that. I would have to talk to him a little bit more extensively about some of the things he has seen, but I think he was able to make out a few more peaks with increased energy than I was. So,
What about the GAGG crystal? A bigger one or?
as far as actual detection goes, I'm not sure because okay. I was gonna say too, the PMT crystal is like the mission sized. So it's the size of the crystal that we were using. So I don't know if there's any wiggle room there as far as to have a bigger crystal or a smaller crystal.
Yeah, there are plenty of things that could be done to improve this, right? The first study had a nicer geometry, but was limited by the data rate of the data acquisition system used with the PMT. And then we used this entire readout for the SIPM, and that improved the readout rate, but at the cost of moving to the sub-Faraday page where the shearing maybe let some gamma rays around, right? So there's I think straightforward ideas how to do it better. It's just ultimately a cost and time constraint.
Yeah. There's a note too that kind of like Dr. Meyer is saying, I mean, the research and the data rate has been improving dramatically because using that red pitaya, we were able to do all of the double pulsing testing for the SIPM within, I would say, probably a week or 2 weeks. So there were a few things that needed to be worked out, but all of this data was gathered within 2 weeks, where over here, it took us 2 weeks just to do 2 of these runs. So the amount of time in which it's taking and the amount of data that we're able to gather is increasing within the group.
Just now, what if you had another crystal of a similar density, but without a high neutron capture cross section, and you did set up the same experimental setup, or you switched out the GAGG with that, and then you'd be able to ignore all other factors and just focus on the neutron capture. Yeah, I did want to batch simulation.
Wait, say that again. So
like it had a scintillating crystal in the same like volume and orientation and the same experimental setup, but that one doesn't have gadolinium, so it doesn't cross-section. It doesn't have a high cross-section of capturing.
okay.
So you could test its ability. You could distinguish its gammas versus neutrons that way.
Yeah, but they're all very slow crystals.
If you really wanted to nail it, would separate isotopes and use one with an enriched in 157 and one depleted in 157.
That would be
right?
perfect.
So, but then again, maybe we can deduce what's going on by just looking at the double pulses, and if they agree in both energy and timing structure is what we would expect. It's pretty strong evidence of neutron detection.
Okay.
Yes.
I have a very basic question. I think it's because I missed some of the slides.
Okay.
So tungsten epoxy as a moderator, right? So I just wanted to know what a moderator exactly does in this case.
So a moderator is going to be to thermalize the neutrons, because the neutrons are going to have higher energies, they're going to be faster, and you want to slow some of those down to be able to get into the GAGG crystal and be captured. So yes, yeah, the tungsten epoxy moderator was used as a test, but it was for the bulk of the research, paraffin was used. But that was just, yeah, that was just a test to see if that would make a good moderator material because of the amount of hydrogens present within it.
The snappy spacecraft, this small CubeSat that we want to launch as prototype detector that has shielding around the detector. That shielding is tungsten loaded epoxy. It's loaded with tungsten to absorb radiation in space, but it still has the epoxy because there's a requirement that no big chunk can re-enter the atmosphere and on somebody's head, right? So you have to make it so that it burns up on re-entry and hence the epoxy with the tungsten powder in it. And so hence the idea that maybe that also moderates. So we wanted to see how well it does that.
Yeah, I have a quite simple question. What makes the GAGG crystal so special for studying neutron nucleus or detecting them?
Or neutrons or neutrinos? Okay, well, for neutrons, it's going to be the high neutron capture cross section of the gadolinium. So that's what I'm interested in, because the gadolinium is a component of the GAGG crystal. Yeah,
The fact that it de-excites most of the time in at least 2 separate steps, and so you get a double valence, right? Which means you have random backgrounds may usually result in single energy deposits, and so if you have a double valence as your signal, you would need 2 random background events in close succession to mimic such a signal, right? And so the double valence signal is suppressing backgrounds from other sources.
But those two different peaks are two different interactions that are happening in the crystal.
Yes, 2 different readouts that are happening of gammas.
But not interactions. It's
okay.
Hitting the gadolinium and exciting it, like Tyler showed in that one slide. And
Which one?
was gamma n means it's more than 1, right? And so in the table you see it can be just 1 de-excitation with the full 8 MeV energy, but that happens only a small fraction of the time, only in 3% or so of the interactions. And then the other whole table listed primary energy and the secondary and sometimes tertiary energy. And so that's the de-excitation to an intermediate state and then to a ground state, right?
Probably a
So,
CD star
yeah,
M5, and then you go down to the M4, the M3, the M2, the M4.
Yeah, without getting into all the nuclear physics details.
Yeah.
There's
Yeah.
different ways.
And I mean, that's why the N is there for the gamma too, is because that doesn't have a set amount. It could be any of these. Yes. Yeah, sometimes tertiary, exactly. So I hope that answers that. I don't know if that was the question exactly. Yes.
Between them though, is that 2 photons, or are you detecting something else and then the gamma, or what are the double pulse? If you're detecting 2 things because it excites it, are you detecting that, or are you just detecting the emission? What are you detecting?
So it's one event being detected twice. So when you have gadolinium 155, the neutron comes in, gadolinium 156 is now in the excited state. That excited state has a now de-excites. When it de-excites, it's going to release one of these gammas. So it is supposed to release, for example, if we go to like number 5 here, it could release this first pulse and then release a second pulse. But these are two different gamma these are two different gamma energies. It's not the same. I guess I'm still slightly confused on the question.
So for example, it releases 6.4 MeV photon, and then you are de-excited not yet to the ground state, and so it can then de-excite further by emitting a 2 MeV photon, or by emitting a 1.8 MeV photon and 0.2 MeV tertiary photon. Right. So you have all these different possibilities with different probabilities.
Because it's going down the energy.
Not for medicine.
Photon rate.
And it's also more complicated because our crystal can only capture with 100% of 1.4 MeV. So,
Right.
so you're seeing a small signal, but it's correlating to a bigger event.
And that's why each row adds to approximately 8,500 or whatever.
Yeah.
We have one more question over here.
Does that answer the question? I guess. Okay.
Like, why did you have
The aluminum Faraday cage just ended up being better. So with the red Pataya setup and the new DAC, the whole setup just ended up being I guess a lot better and blocking out some of that noise that we were getting. And that's the reason we were using the Faraday cage.
Yeah, we are
So-
just a couple of feet from the lunchroom with the microwave, right? And this is just an incredibly noisy environment anyway. Right.
Everything gets tested in
Yeah.
Faraday cage. And
Right.
it's
Yeah, so it's like
repeatable from day to day.
Yeah. And the Faraday cage or the copper one we've had for how many years did we have that when Jared built it? Yeah. So it served its purpose and it was good for the time, but I mean, we also found a better one with time as the experiment goes on and stuff. So
Faraday cage, but it is a smaller volume that doesn't get as much.
talking about absorbing your neutron on a limited basis goes back down the ground? Those gamma rays are emitted random direction, right? Not in a specific direction.
yes.
Theoretically, get better, stronger signal if you have some way to focus the random emissions from the entire crystal toward the sensor instead of just sitting directly on top.
I haven't looked into that and I don't know if us having looked into that, but that's an interesting question.
Well, the gamma rays, of course, produce, light in the crystal, and then you need to reflect the light back to the sensor. So the crystal is packaged in reflecting material, right?
So but photons always end up in the sensor.
No,
They can, they can get absorbed in the material, they can get scattered so many times that they just range out, right? Basically, with some probability. So, the detection for a given event, you don't know which way the light is going primarily, and so it might be more likely to be detected or less likely, but you just do a sample over many events and simulate many events and compare averages.
Well, are you talking about like a amplifier setup, or I guess maybe because yeah. Oh, okay, okay. All right. Oh, okay.
All right, well, that was a lively discussion that ensued. So that means it was a good presentation. So let's thank Tyler again. And we don't have a seminar scheduled for next week. The college has a new dean who has a welcome event next week at this time. So we'll do that instead. But 2 weeks from today, we'll have the next physics seminar talk. That will be on Emily Noether's two theorems and their impact on the development of particle physics. Join us again then. Have a good week. All right. Yeah, that was nice.
Yes, no idea of when.
Yeah, it was.